So today is the last class before spring break, right? And so first, I need to give the public service announcement, right? That if you guys are traveling anywhere for spring break, be safe out there, right? And so, watch out for whatever is happening with the pandemic. Um, and this would, of course, be a good time to get vaccinated if you haven't done so already. And so, obviously, I'm not a medical doctor. I can't give you medical advice, but from whatever I've heard, it sounds like it's worth it. And so, I would encourage you to do that. I understand that Kent State is providing a way for students to get vaccinated on campus. That is just, I think, today and the next few days, today, tomorrow, and maybe a couple of days into next week. And so that sounds like it would be relatively convenient and free. And so if you guys don't already have some other plan to get vaccinated, that would be a good thing to look into. So just want to pass that along, and that sounds like it should be worthwhile. Beyond that, we're kind of drawing close to the end of this semester. And so let's take a few minutes to talk about what's the plan for this course, right? So I guess we have this class before spring break and then 2 weeks after spring break. So about 7 classes after spring break. And we're about finished with chapter 4, but the book goes on through chapter 12. And so there's really a lot there. And that would take us till Christmas, but we don't have till Christmas. So I need to just pick out a few more sections of the book that I think are the most important things for you guys to see as part of a first semester introduction to quantum mechanics. And so the sections that I have picked out are these, right? To say 5.1, which is about quantum mechanics with more than one particle. And 5.2, which is a special case of that for atoms with more than one electron. And then I also want to show you 7.1, which is about perturbation theory. And that means a systematic way of making approximations. So for calculations that you can't do exactly, it's a way to make approximate calculations, with pencil and paper type techniques. So I think these 3 sections will pretty much do it for us for the rest of this semester. And so I will, I'll be covering those today and after spring break. And then after the break, there'll be, I think, one more homework assignment, which will deal with those sections, in addition to the homework that you're working on now about spin. And so that'll be the homework for the rest of this semester. And then there'll be a final exam, again, with this 24-hour format like you had for the midterm. Okay, so that's the plan. Okay, any questions about the plan or complaints or anything else? All right, fine, good. All right, so for for today, let's begin with this section. Okay, so 5.1 about quantum mechanics with more than one particle. All right, and so let me kind of introduce this. Okay, and so if we have more than one particle, that means that we need to think about the position of both particles, right? Or however many particles there are. So we have positions, R1 for particle number 1, R2 for particle number 2, perhaps more. Okay. And then also each particle could have a spin state. So M1, M2, perhaps more. Okay. So that means that in general, you'll have a wave function that depends on all of these variables. Okay. So that means a wave function, psi, which is a function of the coordinates of particle 1. So that's R1 and the spin state M1. Okay. And then it will be a function of R2 and the spin state for number 2, etc., however many there are. And also a function of time. Okay, so this is the general wave function for a system with more than one particle. Right? And then this wave function provides you the kind of information that we've gotten from a wave function before. Okay, and so we would say, if we want the statistical interpretation, we could take the wave function magnitude squared, then dx1, dy1, dz1, dx2, dy2, dz2, however many d's there are for all the particles. Okay, and that is the probability that particle 1 is between x1 and x1 plus dx1, and between y1 and y1 plus dy1, and z1 and z1 plus dz1, dot, 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 right? And in spin state M1, okay, so all of that writing is for particle 1. And particle 2 is between x2 and x2 plus dx2, and between y2 and y2 plus dy2, and between z2 and z2 plus dz2, and in spin state M2. So there's really a lot of information built into this wave function, right? I mean, it includes all of this kind of dependence, right? And it has to be normalized. So for the normalization, right, all the probabilities have to add up to 1. Okay, so we must have 1 is the integral over dx1, dy1, dz1, and dx2, dy2, dz2. So you're summing over all of those position coordinates. You're integrating over all the position coordinates, and you have to sum over m1 and m2, all the spin coordinates of the magnitude of psi. Squared. Okay, so it's a big generalization of the kind of thing that we've had before, right? So you could say, each possible coordinate, right? Each thing that a wave function can depend on, that's all the positions and all the spin states, they all get fed into this wave function. They all go in here. All spin states and positions. And then they all have to get summed over as part of the normalization. So you sum over the spins, which are discrete, and you integrate over the positions, which are continuous. Okay, so that's the general idea. That's maybe a little too much to think about right from the beginning. So let's take a specific case. Okay, so suppose we have two particles. And suppose we care about position and not spin. And for the moment, I'll say, suppose that the particles are distinguishable, like an electron and a proton. So I'll talk later on about why distinguishable is important. But for now, let's just think they are different types of particles. Okay. All right then, so we have then two particles with two positions. And so in that case, we would get a wave function that involves R1 and R2 and time. So, this is already a lot to deal with. Okay, so let's think about that. Okay, so I showed you the statistical interpretation of the wave function, right? But now, how do we calculate it, right? Well, as usual, we calculate it with Schrödinger's equation. Okay? So the time evolution is given by Schrödinger's equation. And so that says, as it always says, that IH bar times the time derivative of the wave function is equal to the Hamiltonian acting on the wave function. Right? That's the Schrödinger equation in general for any kind of system. All right. So now the Hamiltonian, what's that, right? That has to involve both the position of particle 1 and also the position of particle 2. Okay? So we could say that the Hamiltonian operator is going to be the kinetic energy plus the potential. Okay, so So the kinetic energy, that should be the momentum squared of particle 1 divided by 2 times the mass, okay? And then the same for particle 2. So for particle 1, we have minus h bar squared over 2m1 times the Laplacian with respect to particle 1. Okay, so Laplacian with respect to number 1. And so that means the second partial derivative with respect to x1 plus the second partial derivative with respect to y1 plus the second partial derivative with respect to z1. Okay. Then we have the same thing with particle 2. Okay, so that would be minus h bar squared over 2m2 times the Laplacian with respect to particle 2. Okay, so that means the second partial derivative with respect to x2 plus the second partial derivative with respect to y2 plus the second partial derivative with respect to z2. And then we have to add on the potential energy. So the potential energy could be some function of R1 and R2. Okay, so this is the potential energy. And in any particular problem, you'd have to specify what is the potential energy as a function of R1 and R2. There's all kinds of possibilities there, right? So let me first show you the simplest case, right? Well, I should say there are 2 common special cases, one of which is easy and the other not so easy. Okay, so for 2 common special cases. So the relatively easy one is for non-interacting particles. Non-interacting particles means that the potential energy as a function of R1 and R2 is equal to some function of R1 plus some function of R2. Might be the same function or different functions, okay? So what that means is that each particle interacts with an external potential, but not with each other. So, no, not with each other. Okay. So an example of that would be, say, for the simple harmonic oscillator. Okay. So if you have a simple harmonic oscillator with, V of x as a function of x. Okay, that looks like this. Parabola. Okay, so suppose you have a blue particle that goes up and down in the simple harmonic oscillator, and you also have a red particle that goes up and down in the simple harmonic oscillator. And these are ghost particles, right? That could just pass right through each other. They don't even notice each other. They just notice the potential, okay? And so in that case, we would say the potential energy is 1/2 m1 omega 1 squared x1 squared plus 1/2 m2 omega 2 squared x2 squared. So each particle then is feeling the potential energy of the simple harmonic oscillator, but they don't feel each other, not even that they bump into each other, right? If they were bumping into each other, I'd have to put in something that says they can't both be in the same place at the same time, right? So this is for ghost particles that are free to just pass right through each other, don't feel each other. Okay. In that case, in this special case, we can do separation of variables. Okay, so that means for our separation of variables, okay, so we could then assume that the wave function that depends on R1, R2, and T is a product of things, right? And so it's a product of some wave function, I'll call it psi A of R1 times psi B of R2 times e to the minus I energy T over H bar. Okay, let's put that into Schrodinger's equation and see what happens. Okay. It's funny, in my notes, I write it out as if it's obvious and I just skip to the answer, but it's not obvious. So let's put it into Schrodinger's equation and see what happens. Okay. Put into Schrodinger's equation. All right. So Schrodinger's equation is I H bar d psi dt is the Hamiltonian. Okay, so the Hamiltonian is minus H bar squared over 2m. This Laplacian with respect to coordinate 1. And then minus H bar squared over 2m2, Laplacian with respect to coordinate 2, and then plus V1 of R1 plus V2 of R2, each of those things times psi. Okay, so now if we put in the separation of variables assumption, okay, let's see how that works. Okay. So on the left side of this, we have IH bar and a time derivative, okay? So that is here the psi, lowercase psi A of R1 and lowercase psi B of R2. Those things factor out of the time derivative, right? And then we get minus I energy over H bar e to the minus I energy T over H bar. Okay, that looks pretty good on the left side. All right, how about on the right side? Okay. In the first term, okay, we have minus h bar squared over 2m, 1. All right, now we have this Laplacian with respect to the coordinates of particle 1, right? So now when that acts on this product, right, it only cares about the coordinates of particle 1, which are here. Okay, it doesn't care about the coordinates of particle 2. It doesn't care about time. Okay, so the psi b function factors out, and the complex exponential factors out. So we have psi b of R2 factors out the e to the minus I e t over h bar factors out. Okay, and then we need the Laplacian with respect to the coordinates of particle 1 of psi a. Okay, how about for the second term? Okay, so same story there. So minus h bar squared over 2m2 psi a. Okay, so now the particle 1 stuff factors out. Whoops, L2 squared of psi b. Okay. Now what? Now we have the potential energy terms. Okay, so with each of those, I can write it. Here, I'll put the first one on the first line and the second one on the second line. So V1 of R1 times psi A of R1 psi B of R2 is this exponential. And the other term I'll put down on the last line. V2 of R2 psi A of R2 psi B, no, psi A of R1, excuse me, psi B of R2 e to the minus I energy T over H bar. Okay, now how can we simplify this? Okay, well, for one thing, the time-dependent exponential cancels everywhere. It's the same factor everywhere. Okay. For another thing, we can use the normal separation of variables trick, where we divide every term by the product. Divide through by psi A of R1, psi B of R2. Okay, and I'll do that division in every term, psi A, psi B, psi A, psi B. Okay, so these things cancel there and there and there and there, and this mostly cancels. Okay, so now let's see what's left. All right, so on the left side, pretty much everything cancels. What doesn't cancel? The H bars cancel, the I and negative I cancel. All that's left is energy. Okay, so on the left side, we just have energy. On the right side, what's left? Okay, well, we have the minus h bar squared over 2 times the mass. And then 1 over psi A of R1 Laplacian with respect to R1 of psi A. Okay, that's all for this first term. Okay, then the same thing, whoops, excuse me, for the second line, minus h bar squared over 2m2, 1 over psi b of R2, Laplacian of psi b. Okay. And then what? Then there's just plus V1 of R1 and plus V2 of R2. Okay, and now we observe that on the first line, right, for all of these terms here, these terms, this combination depends on R1, not R2, right? The stuff circled there has nothing to do with R2. Okay? Similarly, the stuff that I'll circle in blue here depends on R2, not on R1. So now I can say the usual separation of variable story, right? That is, how can something that doesn't involve R2 and plus something that doesn't involve R1, how can those things just add up to a constant, right? The only way is if they're both constants, okay? So therefore, the red stuff must be a constant and the blue stuff must be a constant, okay? So we would say the red stuff is minus h bar squared over 2m1, 1 over psi a of R1, this Laplacian of psi a, plus V1 of R1. That has to be a constant. Let's call it E sub a. Okay, and likewise for the blue stuff, minus h bar squared over 2m2, 1 over psi b of R2, this Laplacian of psi b, plus V2 of R2 has to be some other constant, EB. And those two constants have to add up to be E. Okay, so E equals EA plus EB. So this is actually nice, right? This is the only situation in which a two-particle problem is not a disaster, right? So that in this situation, we get separate equations, a separate Schrodinger equation, basically for each particle, right? To help you recognize that, let's take the red equation and multiply everything by psi a. So here, I erase this and I multiply through by psi a of R1 equals EA times psi a of R1. Okay. And then here, whoops, you multiply through by psi b. Here, psi b of R2, psi b of R2. Okay, so this is now two copies of the time-independent Schrodinger equation. Okay. So each of the two particles satisfies the time-independent Schrodinger equation. And each of the two particles has an energy. And those two energies add up to make the energy of the total system. Okay, so in this situation, we would say particle 1 is in state A with energy E sub A, and particle 2 is in state B with energy E sub B. And yeah, so then this E is the total energy. So this is pretty nice, right? This is a separable solution, right? So the same way that earlier in the semester, we had separable solutions between position and time, right? And or later we had separable solutions between spin and time, right? So here, this is a separable solution between particles 1 and 2. Okay. So here, this is a separable solution. Okay, but there's always a but you know that not all solutions are separable solutions, right? That some solutions might be separable solutions, but the general solution might not be separable. The general solution is not necessarily separable. Right, so what else could it be? Well, it might be a linear combination of separable solutions. We've seen that lots of times in this semester, right? Situations that are a linear combination of separable solutions. So what that might look like would be a psi as a function of R1, R2 in time. Okay, so it might be one separable solution with a coefficient times another separable solution with another coefficient. So what that would look like, well, so here's one. Whoops. Let's say psi A of R1 times psi B of R2 times e to the minus I EA plus EB T over H bar. Okay, so this is what we just found, right? This is the separable solution where particle 1 is in state A and particle 2 is in state B. Right? But we might also get some mixture of particle 1 in state C and particle 2 in state D. And then the time-dependent factor would be e to the minus I, EC plus ED T over H bar. So we might have, say, 3/5 coefficient times the first thing plus a 4/5 coefficient times the second thing, right? That would be normalized, right? Because 3/5 squared plus 4/5 squared equals 1. Okay? So this would be an example of a solution which is not a separable solution, right? This solution does not have the property that it's some function of R1 times some function of R2. It's a combination of things that have that property, but by itself, it does not have that property. Okay, this absolutely can happen, right? And so, this is actually an important concept in quantum mechanics. Okay, because in this situation, you would say that the state of particle 1 depends on the state of particle 2. And vice versa. Okay, so let's see an example of that. Okay, so suppose you measure the energy of particle 1. Okay, in this state. Okay, so the state of the system is this thing. Okay, and you measure the energy of particle 1. Okay, you will either find that the particle 1 has energy EA, which goes with state A, or it has energy EC, which goes with state C. Okay, so we could say with probability of 9/25, that is 3/5 squared, you will find that particle 1 has the energy EA. And with probability 16/25, you will find that particle 1 has energy EC. Okay, so far, that's just like what you've seen earlier in this semester, right? In this semester, right, you've had lots of homework problems that are, suppose you measure the energy of a particle, what are the possible energies and the probabilities of those things? Okay, so far, this is all the same as before, but now there's an additional feature, okay? That is that if you measure the energy of particle 1 and you get EA, then you have to be in this state, which means that particle 2 has energy EB. So in this state, if you make the measurement of particle 1, then you can say for sure that particle 2 has E sub B. And if you find that particle 1 has energy E sub C, then you know for sure that particle 2 has E sub D. That is a weird quantum mechanical phenomenon, which does not have an analog in classical physics. Okay? And the word we use for that is that the particles are entangled. Okay. So an entangled state is a state that is not a separable state, right? Entangled is basically not separable. That is, you cannot write the state as a product of single particle wave functions. Product of single particle states. Okay, so a product would be, just this or just that, right? But if you have a combination of products like this, then you get this quantum mechanical phenomenon of entanglement, that the state of one influences the state of two and vice versa. So this is an interesting feature, a surprising feature that happens even with the simplest possible case of non-interacting particles. Okay. Now, in real life, it can be way more complicated than that, right? In real life, the potential energy often is not just the sum of a potential energy for particle 1 plus a potential energy of particle 2. So I'll just mention that, even though I won't actually calculate anything. Okay, so the other special case that's common is what the book calls a central potential, or people often call it a central force potential. And that is a situation where the potential energy as a function of R1 and R2 is equal to a function of the distance apart. So you take the difference of R1 and R2, the difference of those vectors. Okay, so this is R1 minus R2 vector is the vector that goes from one to the other. And then if you take the absolute magnitude of that vector, that's the distance between one particle and another. Okay, so this is the distance between 1 and 2. And this, this form of the potential energy, that's the normal thing for Coulomb's law, for example, right? The Coulomb's law depends on the distance between two particles, or gravity depends on the distance between two particles. That sort of thing happens a lot. In this case, we would have to say that the particles interact with each other. In this case, the separation of variables doesn't work. And this is a difficult situation. I'll just say this is common and difficult. And I'm not really going to speak about it more. Yeah, and so this is a big thing in more advanced courses and more advanced research, is how to deal with problems like this. But I'm not going to talk about that. So let me talk about something else instead. Okay, what I am going to talk about now is what happens if the particles are not distinguishable. Okay, so you remember, I said way back in the beginning of this class, right, that we're assuming that we have distinguishable particles, meaning different types of particles. And this is actually an important concept in quantum mechanics. Okay, so let me say a few things about that. Okay, so would say distinguishable versus identical particles. So here's a difference between classical and quantum mechanics. In classical mechanics, we might label the particles. So they would be, like pool balls with numbers. Okay, so we could say, here's a particle, it's moving somewhere. Here's another particle, it's moving somewhere. And they have numbers, 1, 2, okay? In quantum mechanics, the idea is that we cannot label the particles. That there really is no distinction between them. They are particles if they are the same type, okay? So, I mean, if they're different types, if one's a proton and one's an electron, then you can say, oh, look, there's a proton, there's an electron, okay? But if they are the same type, then they really are indistinguishable. Okay, so what it means for particles to be indistinguishable is that we cannot have a wave function that says particle 1 is in state A. And particle 2 is in state B. Because that's sort of making a distinction. It's identifying, here's one electron that's in a certain state. Here's the other electron that's in a different state. But there's no difference between the two electrons, okay? And so instead, the wave function has to be neutral between the two particles. So that means the wave function can say one particle is in state A, one particle is in state B. But which particle is in state A? Which particle is in state B? I don't know. They're indistinguishable, right? And so the idea is the wave function can say there's one in each of the states, but the wave function cannot say which one is in which state. Okay. So how can you do that? Okay. How can it be neutral like that? How to do that? Well, there are two possibilities, okay? One is that you can combine two different wave functions and just add up both of those possibilities, okay? So you could take psi A of R1 times psi B of R2. Okay, so this combined wave function says, all right, particle 1 is in state A, particle 2 is in state B. Okay. And then we could add plus psi B of R1, psi A of R2. Okay, this is a linear combination of two separable states. And one, the first half says number 1 is in A, number 2 is in B. The second half says number 1 is in B, number 2 is in A. Okay, and if you add those things together, that makes a combined state. So we could say, let's make a combined state that is psi plus, I'll call it, of R1 and R2. So, which is some factor times those things. Okay. That is a symmetric combination. There's another way that you could achieve the same thing. Okay. The other way that you could achieve it is you can take this product, psi A of R1, psi B of R2, and subtract the other one, psi B of R1, psi A of R2. And that times a normalization constant. That would make a different way of combining the two. And we'll call that psi, whoops, not one. We'll call that psi minus. Okay. So this is what people would call an anti-symmetric combination. Okay. So this is a combination where if you exchange the indices for 1 and 2, the wave function changes sign. But maybe that's okay. The wave function can change sign because there's still the same probability, even when the wave function changes sign. So these are two ways that the wave function can be neutral. A wave function can be agnostic about which particle is in which state, right? These are two ways that you can have the same probabilities if you interchange the particles. If you switch around which one you think is particle 1 and which one you think is particle 2. So these are two types of possibilities, okay? And then you might ask, well, which of those two things happens? And the answer is that it depends on the type of particle. There are two types of particles when it comes to this kind of a question. Okay? There is a set of particles called bosons, where the wave function must be symmetric under the interchange of what you call 1, and 2. And there is a different type of particles called fermions, where the wave function must be anti-symmetric under the interchange of 1 and 2. Okay, so that means if you have bosons, you must have a state like this one. If you have two identical bosons, they have to have the first kind of state. And if you have two identical fermions, they have to have the second kind of state. Now, how do you know which kinds of particles are bosons and which kinds of particles are fermions? Okay, well, there is actually a proof of that comes from relativistic quantum mechanics. Okay, so that is a more advanced version of quantum mechanics than what we have in the first semester. But I'll just tell you a result from relativistic quantum mechanics. The proof is that what the distinction of boson versus fermion depends on the spin of the particles. That is, if you have an integer spin, then you get bosons. And if you have a half integer spin, you get fermions. And so that would be, integer spin combines in this symmetrical way. And half integer spin means combining in this anti-symmetric way. So an integer spin, well, of course, that's any integer, right? So a spin of 0 or 1 or 2, etc. A half integer spin means spin half or spin 3 halves or 5 halves. And so in particular for electrons, I've told you that electrons have spin of 1/2. And so electrons are fermions. Electrons have this property that they need to form an anti-symmetric combination, not a symmetric combination. Just to tell you one bit of vocabulary, maybe, and then I'll wrap up for today. For one bit of vocabulary, this distinction between bosons and fermions and symmetric versus anti-symmetric states, this is called statistics. I'm not exactly sure why it's called statistics, but people call it statistics, okay? And so this phenomenon of bosons, this goes by the name of Bose-Einstein statistics. And the property of being fermions, this goes by the name of Fermi-Dirac statistics. Okay. And then this, this theorem of relativistic quantum mechanics this thing is the connection between spin and statistics. All right. So this is telling us that for identical particles, either identical bosons or identical fermions, that we have to have an entangled state, right? This thing is entangled, right? This is entangled, right? That the nice separable state, it works for distinguishable particles, but it doesn't work when we are required to follow this connection between spin and statistics. And so, you know, the entanglement turns out to be an important feature of quantum mechanics. And in the next class, I'm going to show you a couple of examples of how the entanglement, you know, actually changes predictions for experiments, right? And so there are real applications of this. And so even though it might seem very abstract to think that, you know, there's a wave function that has some symmetry and, you know, is it positive, is it negative? Maybe you think, who cares, right? But in the next class, I'll show you some reasons why maybe you might want to care about that. But for now, I think this is a good breaking point for spring break. Okay, so I'm going to stop here even a few minutes early, and let's take a break for now. So enjoy your vacation. So you get a week away from quantum mechanics, and then I will see you then for the grand finale of this course in a week from Monday. All right. Thank you, guys. I'll take a break now and, of course, answer your questions if you have any, and otherwise see you in, what, about 11 days. Okay, so long.